Okay, please welcome our first speaker, Dr. Cervenka.
So, ladies and gentlemen, I'm very happy that I can be here in New Orleans at ACI and in this session about artificial intelligence and machine learning. So I would like to introduce you the work that we are doing on using AI in connection with nonlinear finite element analysis, monitoring for structural health monitoring and assessment. So just very briefly what we are doing, I come from Czech Republic. Our company is producing technology, mainly software for advanced analysis and modeling, like you can see here, of the structural behavior, considering the cracking, reinforcement yielding, all the important nonlinear effects in reinforced concrete structures. So we use this in the context of digital twins, which is a very famous or modern term now. So what we want to do is we want to combine the results from the real structure and the monitoring of the structure and the virtual twin. When you put it together, then it is often called digital twin. But to tell the truth, to have a true digital twin, there should be a very runtime, extensive communication between these two. So this is still something we are a little bit developing and working on. So how do we use AI? So on one hand, we have our structure with the monitoring applied there, getting some monitoring data, typically in terms of some strain readings, and on the other hand we have our finite element model where we can model the real structural behavior. And as you know, every time we make nonlinear analysis, we actually end up with many analyses, sometimes just to tune up the model, but then we can also make some parametric sensitivity analysis, so we can produce a lot of results, and we can use these results to learn our neural networks. We are using the artificial neural networks, and we are using them for two tasks. First task is to help us with the parameter identification. That means when we have the data and our model, we need to make sure the model is reproducing the data. The material parameters that we are using in the model are representative and produce accurate results. So for that we can use the artificial neural network. And the other task is then, once we have a model which is calibrated and we have the data from the bridge, we can train again the neural network to give us quickly, because of course we can, based on the monitoring data, we can run some analysis to reflect what's happening in the bridge, but that takes time. Nonlinear analysis takes time. So in order to be able to do this runtime, we can efficiently use this neural network model, which gives the answer immediately. And the typical quantities we are trying to extract is, for instance, the bridge utilization ratio, maybe the reliability index. Then even we can go deeper to get some information what would be the stresses in the structure for the given monitoring reading. So this is the task. Yes, so I told you we have this neural network model. So this is a typical way how it looks like, and we always have to divide our sets to a training set and to evaluation set, and we train it based on the results from a numerical simulation. What we can also use, and it is sometimes actually more advantageous than the neural network, is the polynomial Gauss expansion. So basically there we can create a model where we need to calibrate these coefficients. These are these polynomials which are orthonormal with respect to the joint distribution, and we use some efficient algorithm based on the least angle progression method. So this is here is some diagram of how this works. Of course, it looks complex, but you can program it and then it works. And now let me show some applications. So I will show two examples. One is a very simple one, actually a small bridge. But on the other hand, this is a nice bridge because you can nicely play with it. The nonlinear analysis doesn't take so much. So it is a good example to evaluate it. On the other hand, this bridge has problems because it is very old. You see it's more than 100 years old. It's a railway bridge, so it is also easy to determine what are the loads coming because we know the weight of the locomotives. And here you see the monitoring setup. In this case, we use some fiber optics sensors. And you can see there are some damages. Here you see some water leakage. There are some cracks in the longitudinal direction. From a structural point of view, it's a simple structure because it's a simply supported slab. And the slab is a concrete slab, and inside you have these steel I-beams. Another structure I'll be showing is a little bit more complex. It is a bridge which is part of this whole bridge assembly. So it is somewhere here, this part that we modeled. It was constructed in 1970s. And it's a double span bridge, and it's reinforced concrete, yeah? So no pre-stressing. And in this case, a little bit more advanced monitoring was used. This shows the strain gauges installed at the top, at the bottom. There is even some laser rangefinder, which is nice because it can determine the number of axes of the vehicles passing the bridge, the speed even of the vehicle. So you can get nice information then about the weight distribution of weights of the bridge. You can even see what was the speed of the traffic passing the bridge. Of course, it needs to be calibrated. So to calibrate the system, first you need to have trucks with the predefined weight to calibrate the system. And what we want to do, this shows what we can do with the finite element analysis that we want to somehow put together with the monitoring. So we also try, this is showing some long-term predictions of the structure in the future considering the corrosion model. So just to give you an understanding what you see on the figures. So this is the behavior or simulation of the bridge up to 150 years considering a chloride attack. So here you see this top figure shows you during these 150 years how what is the chloride concentration at the depth of reinforcement. So basically in the model, what we do, we apply some boundary conditions or surface conditions of the chloride concentration, and then we calculate how the chlorides propagate. And actually we don't use like a 3D model. It's a very efficient because the chloride propagation, actually, if you think about it, is just a local phenomena. You don't need to make a whole 3D analysis. So we are using just a one-dimensional propagation model for the chloride progress or carbonation progress. When it hits the reinforcement, this is what you see. We have discrete model of reinforcement. We know at each point what is the distance of reinforcement from the cover, from the surface, what is the cover thickness of the cover. So we can, when the critical chloride concentration reaches the reinforcement, corrosion is activated, and you can see here how the corrosion is increasing. Red is full corroded, blue is intact, and you also see how this corrosion is affected by the presence of cracks. So the model, of course, takes into account if there is a crack, mechanical crack, that the corrosion, or not the corrosion, but the chloride propagation will be faster. Yeah, this shows the cracks in the interior, this shows the cracks on the surface. And when we do that, we always load the structure to failure at certain times. So here you see the behavior of the structure intact after 50 years, 100 years, 150. So you see how the structural strength degrades due to the corrosion. We can plot it in time, and out of that we can get some information what will be the expected life of the bridge. So all this is used in some kind of platform, online platform, where we have the projects, and we can then output what would be the utilization of the bridge when we have some traffic events on the bridge. It can be in various types of plots, also maybe in this scattered plot, which shows on the horizontal axis, I don't see it now, the weight, yes, and this is the utilization for the various weights of the tracks or traffic crossing the bridge. Well, so how do we merge it together? Yes, so this I try to show on this slide. So we have the data from the monitor, and of course it depends when you install the monitoring, but typically the monitoring in this case, for instance, was only recording the events when something was passing. So to that we need to add other deformations, definitely from the self-weight of the bridge, and then maybe from temperature effects. And this, of course, we don't know. So we can use again the numerical model to calculate that. And when we have the total deformation, then maybe we can go to these low displacement graphs and determine what is the utilization that we can then plot. So of course we can make some estimates based on the numerical model, how to estimate these quantities. But here it is the situation where we can use the neural network as a kind of a surrogate model. So that's what I think I want to show on, I will come to that later. So we have these two ways how we use this neural network. One is to identify the parameters, and later on I will show you on that previous example how we use it to determine these deformations from the temperature. So now some analysis how this is accurate and how does it work. So this is one situation where we use it on some simple example with experimental data that we can see how the neural network is accurate in predicting or identifying the material parameters. So here you see we tried some data sets. You see that this is data set A was with 100 analysis, this was 400, this was 1000. Of course, then we obtained various low displacement curves. This would be the experimental result. And we investigated various types of the neural networks. Here is the convolution neural network that's often used in digital image processing. The dense neural network, this would be the typical neural network, very simple one, where all neurons are connected with all neurons in the other layer. And then there are also these explainable models, which are more advanced, and the idea is that they can help you to understand, or the neural network should help you to understand why you are getting certain results. And it is actually interesting to see the various accuracy. Actually, it was interesting to see that the best one was almost this dense neural network. Also good one was this LA Mayan. But it's better to see here. So it is also interesting how it is able to predict some quantities. Yes, it very much depends also on the structure. So for instance, this structure we used, which was failing in shear, there was no dependence. You cannot use it to determine compressive strength. Yes, compressive strength was totally not irregular or not cannot be used even for the 1000 cases. But especially for Young's modulus, it is pretty good. For tensile strength, it is starting to be good, but you need a little bit more analysis. So now about this other application of the artificial neural network, it is for this surrogate model. So we want to use the artificial neural network actually to replace our nonlinear analysis to be able to get quick, fast, rapid results. So here you see some results, again for the same example, using 100 cases, 400 cases, and I don't know if you can see here, so this is trying to predict the results by the neural network. The correct result is the solid line, the predicted result by neural network is the dotted line. It is actually not very bad, yeah? It is pretty good prediction. But still, let's say in this 10-15% accuracy. Now I am coming back to this second example, and I told you that we want to use this numerical analysis to train the neural network as a surrogate model to determine what are the deformations from the temperature. Because this is what we know, yes? We are measuring maybe the passing of the train, but we don't know what are the deformations from the temperature that we should consider also in the total assessment. So what we did is that we take the temperature readings, typical temperature profiles, so we can take concrete temperature profiles for the given location. Either we have a sensor from when you monitor, you typically can have also temperature sensor, or we can also go to the intranet and download the typical meteorological data for that particular location. And what we did in this case, we always take temperature at certain point. We take the history there for previous 24 hours, and then the average for the previous 2 days. And we use that to train the network and then to obtain the strain at the sensors. And when you do that, you get quite nice results, yes? So it shows the prediction of the strain. So this is, let's say, the variable value, this is the estimated value, and of course you should have this kind of linear relationship when it is perfect prediction. So we can train it to predict strain in the sensors, and then we can also train it to predict what would be the crack width, maximal stresses in concrete or in the steel. And this is then what we plug in our that monitoring platform to be able to provide this utilization when there is a train passing the bridge, and we can also provide some engineering quantities like the expected stress in the steel or the crack width. Oh no, I'm sorry, this is also the stress. This is in the top flange, this is in the bottom flange, and this is the profile or the evolution of the crack width from the passing train. So this is, I would say, our ongoing work. Yes, we are still developing this and trying to apply it in some practical cases with structural health monitoring. So with this, I will summarize. So we are using this digital twin, combining monitoring with numerical analysis, using our software Athena, and also we are using this durability model to be able to predict the life cycle, basically, of the structure. And our machine learning we use in two ways. One is for the identification of the material parameters to help us calibrate our numerical model based on the monitoring data, and then for providing real-time, fast, rapid data during the monitoring. And for that we use this surrogate model based either on neural networks that I was discussing mainly today, but we have this other possibility with the polynomial cows, which actually sometimes brings even better results. So thank you for your attention.
Thanks so much for the great presentation. So we can have some time to get some questions. Yep.
Thank you for a very nice presentation.
Thank you.
Thank you for a very nice presentation. Some of the things that come up with machine learning more recently as this term physics-informed, physics-based machine learning models. I was wondering if your model does that, or if it will or can do in the future.
Yes. Well, it doesn't. As I told you, we played with these neural networks. We have not tried really this physics-based. Yes, because then I'm afraid with the physics-based, it may be too specific to a particular bridge. Yes. So we tried, and in the end, we came up that the best one was this, this dense neural network, which is the most traditional and simplest one, so to speak. But of course, it takes more time to learn, for learning. But we have not tried this physics. But We are also thinking about it, yes, but there is a little bit difficulty how to define it so that it will represent the physics of the bridge, such that it is general for other bridges.
Yeah, thanks for the answer. And any other question? I have a quick question. So you showed me the real-time ANN, sensing data, time history data. From my experience, the data influx is very large. So how do you deal with that large, say, gigabyte or terabytes for one day, I think? I don't know. How did you make a compact form, or just did you data process first to feed into ANN?
Well, this is the problem of the monitoring company, yes, so to speak. So the monitoring company who is producing the data should filter them out. Yeah, they have to filter out the noise and also have a proper sequence, yes, because in this case, when you monitor, you may have different reasons for monitoring. This time it was basically monitoring of individual events, so we could make a dense sampling. But if you monitor over a long period, then of course you cannot have such a sampling. But then if you have a monitor for years and your sampling is not very dense, you may miss the traffic, yes? So this is of course something we have to set it up, and maybe it's done with the cooperation with the company who is monitoring it. Yes.